you, Ramon. Thank you for the nice presentation. I hope we are all energized and ready for a new attempt of understanding minimal Kitaev chains. Thanks to the previous speaker, I don't need to really make a long introduction. I can skip basically half of the presentation, but still I want to make some statements about how to make Kitaev chains and how to tune them. Well, first let me start by thanking my collaborators, and especially these two people that are highlighted. So Athanasios Sintzis, who was a PhD student in Lund, and Michel Pino, who is actually in the audience. So these guys were the important people in the project, so they carried most of the project, and they did most of the calculations you are going to see in the next few minutes. Okay, nevertheless, I decided to keep a little bit some introduction because I want to give my personal point of view. Srijit made a very long introduction about Majorana states in nanowires, introducing the controversy very nicely. But let me say that in my point of view, there are signatures that have been measured of Majorana states, mostly in the form of low energy states at the end of the wire. But what prevented this field to actually proceed to farther and make qubits and actually go towards braiding and showing non-abelian statistics is that we have very little information about what is going on in the bulk. We don't know if the bulk is a disorder. We don't know if there are many Majoranas that are appearing inside due to the breaking of the wire due to chemical potential fluctuations, for example. The alternative is to actually go the other way around. So instead of trying to make a very long wire, why don't we actually take a system that we understand very well and try to make artificial chains out of it. And the system we know very well, they are actually quantum dots. So in the next few minutes, I'm going to focus on the minimal version of the chain that is actually two of these dots. Okay, I hope you are not sick of seeing the Kitaev model by now. This is already yet another slide. As it was previously introduced, this is the minimal model to understand topological superconductivity. It is a spinless chain where fermions can actually jump between neighboring sites or pair between neighboring sites. So this is a p-wave pairing amplitude. And the nice thing is that under certain conditions for the T and the delta and also the chemical potential of the dots, two Majorana bound states appear at the end of the chain. And actually, they are perfectly localized in this model if T is equal to delta and the chemical potential is equal to 0, which means that they live only on the very last side of the chain. And that's true if we reduce the size of the chain, and that's true even if we use only two quantum dots. And that's the so-called minimal Kitaev chain that was previously introduced. So this is the device is schematically that's really introduced. Yeah.
Connecting it to the previous talk. So the number of sites have to be even, right? Even number of
No.
quantum dots or odd?
No, it can be even or odd. Actually, if you want to do, it turns out that if the number is odd, it becomes a little bit harder to tune for whatever technical reason. But it can be both even or odd. At some point it doesn't really matter, right? Because 50 and 51 is going to be the same, right? But it seems that tuning 2 is easier than 3, and 4 is easier than 5 for whatever technical reason. Yeah, by the moment we stop at only 2 of these dots that are tunnel coupled to a superconductor. And the superconductor only mediates the coupling between the 2 quantum dots. So for instance, if we have an electron in one of the quantum dots, this electron can actually jump from one side to the other by occupying a virtual excited state in the superconductor. And that plays the role of the hopping between nearest neighbor. But also we have, so superconductors are a source of Cooper pairs. So we have 2 electrons in the quantum dots. These 2 electrons can recombine in the superconductor and then leave the quantum dots. And that plays the role of the delta of the pairing potential. And as you have seen, the spin of the quantum dots actually precesses. And that's a requirement to get into the sweet spot that happens when these 2 amplitudes are equal. So we need to mix a spin to make these 2 amplitudes the same. the nice thing about these Majoranas is that even though they are not topologically protected, even though they are supposed to disappear whenever there are fluctuations of the parameters of the model, they still preserve Majorana non-abelian properties. So for example, if we exchange them, we expect to see non-abelian properties. And that's, in my opinion, one of the most exciting dimensions of this minimal Kitaev change. But before proceeding to that, let me introduce the first question we asked ourselves, because of course the Kitaev model is nice, but you know, it's not a complete model. In quantum dots have interactions. Of course, we cannot fully spin polarize quantum dots because otherwise we're going to kill superconductivity. And also, spin-orbit coupling is not explicitly included in the model. So the question is, can we actually get Majoranas considering these conditions? And well, to answer that question, we made a model where we consider 3 quantum dots that are tunnel coupled, and actually the middle one is coupled to a superconductor. So there is some induced pairing that only lives in the central superconductor. And this model, let me say, that includes interaction, finite Zeeman field, and spin-orbit coupling. So in principle, it contains all the minimal ingredients to understand this question. And the first thing we realize is that, strictly speaking, there are no Majoranas in this model. It is not possible to find a zero energy state with a purely Majorana wave function. However, there are spots where the Majorana wave function is very close to the proper Majorana one. So the wave function behaves really pretty much like the Majorana. And to characterize how Majorana-like the ground state is, we use what is called the Majorana polarization. And that's nothing else than a quantity that quantifies the degree of localization of the Majoranas. So if Majoranas are delocalized, they live separated in different dots. That means that this MP, the Majorana polarization, should be 1, while if they start to overlap, the Majorana polarization is going to reduce, and then it's going to tend to 0 whenever 2 Majoranas live in the same dot. So we have 2 requirements to get Majoranas. First, we need the energy degeneracy. This is the energy ground state. So this is the gap between the ground state and the first excited state with the different parity as a function of the level position of the quantum dots. And the thing I want you to see here is that there are actually wide regions where the ground state is actually degenerate. That's the place where we want to tune the system. The second thing is the Majorana polarization, which actually peaks around this region here, and it gets a value of 1. We can make them overlap, and we find there's actually 2 sweet spots. So great, that's consistent with experiments. And let me say that this calculation were done using experimental parameters as much as we could. And of course, we can prove it using spectroscopy. We can just attach leads and see what happens. But of course, you know, depending on the resolution, the Majorana sweet spot and the other sweet spot may look slightly similar, depending on resolution. So the question is whether we can do that a little bit better. And the answer is yes. To me, non-local conductance is a better proof of the Majorana properties. Why? Because with non-local conductance, we are proving the T and the delta explicitly. So if elastic co-tunneling dominates, if we inject an electron from this side, it will tend to just go to the other side, to the other lead automatically, leaving by the other lead. That means that the conductance should be actually negative. The non-local conductance should be actually negative. So we have current going out through the left lead. On the other side, if cross Andreev reflection dominates, that means that an electron that is injected from the right side will tend to pair with another that comes from the left one. And that means that the non-local conductance should actually reverse. It should actually have a different sign. And actually at the sweet spot, we expect an alternation between positive and negative conductance, where the sweet spot is just centered at the middle. So that's the charge degeneracy point. And well, let me say that we got really excited because at the same time we were wrapping up there was this very nice experiment by in the group of Leo Hoven where they actually show more or less this pattern. I think this was reproduced by the previous speakers in 2DEX in a beautiful experiment. So it seems that so far everything is consistent. And actually, as we have seen before, people is proceeding to more and more complicated geometries, including 3 dots, and why not going to 4, 5, and scaling that up, right? And this is a comparison of what we expect in, well, in theory, and the very nice experiment by Alberto. But the question is, how can we actually characterize the state of the system? If we learn something from the Majorana field, is that conductance is not enough. We need to do something else, right? And the easiest thing we can do is to attach a quantum dot to one side to prove the Majorana localization. But first of all, let me explain you what happens when we detune some of the quantum dots. So if we start at the sweet spot, we expect to have one Majorana on one side, one Majorana on the other side. Now, if we detune the quantum dot on one side, what happens is that the Majorana actually starts to leak in the opposite quantum dot, meaning that Majorana polarization is going to be very low in the right quantum dot, and it's going to be still 1 in the left one. So the same happens, of course, if you detune the other one. And actually, if you want to get rid of the energy degeneracy, what you have to do is to move both quantum dots or to tune T and delta to different values. So the question is whether we can actually prove all this kind of recipe to improve our confidence on the Majorana interpretation. And the answer is yes, because if we put a quantum dot on one side, this quantum dot can couple to the Majorana here, but eventually it may also couple to the red Majorana when it leaks to the other side. That means that if we are purely localized Majoranas, we're going to find a 0 energy state. That means when we do a spectroscopy, we're going to find a 0 bias conductance peak. That's good? If we detune the dot that is coupled to the measurement dot, we're going to find exactly the same thing, because what's going to happen is that this Majorana is going to leak in the other side. We don't have resolution of what's going on the other side. We may have resolution if we add another quantum dot, but let's keep it simple by the moment. Yeah, good. But actually things change, because if we just detune the other side, now we have 2 Majoranas living on the same, and the quantum dot now can mediate coherent coupling between the 2. So we couple 2 Majoranas, we create a fermion, and then basically we split the ground state degeneracy. And actually the ground state degeneracy splitting becomes maximal whenever the energy of the quantum dot aligns with the energy of the Majorana, so with the chemical potential of the superconductor. And actually, if we now consider the situation where T is different from delta, we get this bow tie-like shape, where there is a splitting whenever the quantum dot is disconnected or is very high in energy, so it's basically not affecting the system. And then we get crossing to 0 energy, and that's due to symmetries of the problem. Well, these are the calculations we did. So for a high Majorana polarization, we see a 0 energy state that actually sticks and persists for all values of the level energy. While if Majorana polarization starts to be small, that for example, due to a finite Zeeman field or due to a misalignment, we start seeing this diamond-like shape. So there is an eye opening there. And actually, we find that a Majorana polarization and splitting is correlated. So that might be a way to test Majorana polarization. Okay, good. So now we know how to tune the system into the sweet spot. We know how to prove the sweet spot. Another question is, can we actually do something interesting with that? And well, to me, the most interesting experiments are quantum coherent experiments. So whether we can actually play qubit games or braiding games with this kind of system. But before that, we need to understand how to initialize the system, right? If we want to be coherent, we need to deterministically initialize the system in a given state and be able to measure that. And initialization is rather simple, because depending on whether we detune the dots symmetrically or asymmetrically, we may load 1 electron or 2 electrons in the system. And that means that we can initialize in the odd parity or in the even parity state. We can bring the state to the sweet spot, and what happens is that in both cases, there is in average 1 electron in both of the dots, meaning that the system has no charge dipole in any of the two states, meaning that we have gained some protection against charge noise, for example. Of course, this is true only on charge noise affecting the level the level of the quantum dots, but not on the one affecting the T and the delta coupling between the quantum dots. Of course, that means that we cannot detect the system. We cannot detect the state of the system if we measure only at one side, at the sweet spot. We would need to actually couple both quantum dots to be able to determine the state of the system. Well, then we can do quantum coherent operations, but for that we need to double the system, right? Because it's not possible to make a qubit based on a single system with even an odd fermion parity, because if we consider this is a closed system, there is no way we can add a single electron. That's not included in the model. That's not included in the system. So we need to include a second state, and the state of the qubit is going to be whether the left and the right states are both in the even or both in the odd parity states. And actually, depending on the Majorana polarization, these two states may split, may or may not split depending on how good the Majorana polarization is. So good, in principle, this qubit can be operated by driving the coupling between them. So that's conventional qubit games. For example, they do that in charge qubits. And then the question is how to measure the state of the system. And well, that's rather easy as well, because we can detune only one side, pick one electron from this side, and actually measure the state on the other side. And depending on whether we measure no electrons or one electron, that's going to be the even or odd parity state. Okay, let me just introduce what we named the Kidmon. So this is the minimal Kitaev Trasmon qubit, one can imagine. So this is a Josephson junction, a conventional Josephson junction put in parallel with the minimal, so two Kitaev chains that are tunnel coupled. And actually, well, we analyzed this system, and what we find is that, well, the spectrum is nothing else than the Trasmon spectrum, but it gets double. Actually, it gets double because of the parity of this state. And actually, what we found interesting is that there are the spectral holes. This is the microwave response, and at the sweet spot, there are regions where the transitions are actually suppressed, and that's, in our interpretation, a signature of the 4-pi Josephson effect. I'm not going to talk a lot about it because Mitchell has a very nice poster that is going to present in a few hours, I believe. But let me just highlight that we developed, or actually he developed a way to measure Majorana polarization by looking at the microwave response. And this is just saying that our expression actually works pretty nicely to determine Majorana polarization. So that's actually a direct measurement of the Majorana quality of the system. Okay, let me just conclude by saying a few words about braiding, because, well, something that is missing in the field is to actually show non-abelian statistics, show that non-abelian quasiparticles actually exist, and Majoranas are non-abelian quasiparticles. So we analyzed 3 different braiding protocols based on charge transfers, so shuttling electrons between the central dot and the left and right system. Measurement-based braiding, so based on measuring the parity of Majoranas coupled to 2 detectors that here are up and down, and also the hybridization-based braiding. So this is a protocol that shuttled, that aims at moving Majoranas in real space. And let me say that out of the 3, in my opinion, it seems that this last one is the most promising one, and that's the one I'm going to concentrate. Well, for that, we make a very simple model where we consider 2 Majoranas, but we consider also that the wrong Majorana can live in the other dots. So there is one Majorana leaking with an amplitude that we call delta, essentially. And the protocol is rather simple. We start with the tree system. We couple this with a tune, the upper Kitaev chain. That's where Kitaev chains are actually advantageous, because it's very easy to detune them. So just move 2 quantum dots up. And then we initialize the left and right, for example, in the 0, 0 state, so in the even state. It doesn't really matter which state we pick. Now I'm going to put some colors in the Majorana so you can follow them. Now if I switch on this coupling while bringing this Majorana to the sweet spot, what is going to happen is that we are going to create a long and effectively long Kitaev chain where there is going to be one Majorana here, one Majorana there, but we haven't really leave the red Majorana untouched. Now we can do the same with the red one. So we connect this one. So now this is the long Kitaev chain with the Majorana that is there. And now the red one has to move to the other side necessarily. And we can actually go to the initial condition. And what we find is that the green Majorana finally goes to the other side, and we have actually exchanged them. And numerically, it seems, and then we can measure the state of the system where we expect that from even state, the system has evolved to linear superposition of even, odd, which means that there is with half probability a Cooper pair has split and ended up in the left and the right system. Okay, these are the numerical results. This is the result for a single braid, and as you see, it works for a rather large parameter space, which was initially surprising to us. And the reason why it works for this relatively large delta range is because the single braid is not sensitive to the dynamical phase. So whenever we start to make the protocol slower and slower, this dynamical phase starts to pop up, and then we see that the region actually decreases with delta. But actually, the dynamical phase is very evident and actually pops up when you do a double braid. So we actually make a full exchange of the 2 Majoranas. And here you see that only works for a very narrow region around delta. So that's hopefully within the range of reachability in experiments. And with that, I would like to finish by summarizing the main points of this presentation. So I have talked about fine-tuned Majoranas or Pullman's Majoranas in minimal Kitaev chain using realistic models, mentioning also how to detect them. I have also talked about Kitaev qubits, although I would like to say that Mitchell has a very nice poster, so go and ask him 1,000 questions if you're interested. And also I have talked about quantum coherent experiments, including braiding. And with that, let me thank you for your attention.